Yes, I think it's 1 minute past now. So good morning to everyone and welcome to this DigiPro webinar on MEMS strain gauge sensor for structural monitoring. This speak is given by Guido Sordo. So we're looking very much forward to hear what you have to say, Guido. So please just take the stage.
Thank you very much, Frode. So I will share my screen now. Yes. So my speech will be about this new concept that we are developing at the moment here in SINTEF, in a collaboration between SINTEF. Now it's actually one big group, of course. So it's basically among us, previously known as MINALab and demanding environment, basically. And now we are under the same group, so smart sensors and microsystems. So I will start presenting the people that actually make it real. So here is basically the small team that is working on this topic, on this string gauge activity, in which I'm from MINALab and all the other guys are from demanding environment. And all of us have a different competence, more related to readout electronics or mechanics or bonding technology. So we end up to create a really nice and comprehensive team that cover all the things that I will talk about today. And of course, I need also to thanks all the people that works in our lab, in our laboratory here in MINALab, which makes the concept that we had in mind into reality, into a silicon brick that can be used as a sensor. So let's dive into this. So I moved here in Norway 4 years ago, and more or less in the same time, there was a big accident in Italy in which a bridge on a highway in Genova basically collapsed without any warning, without any apparent reason, let's say. So this was a failure that end up with more than 50 deaths and several hundred of injured. And that's basically the origin of this failure was basically a lack of maintenance in the bridge. And it's not so far away. Here in Norway, we had a similar accident in which a bridge collapsed. This is a complete different bridge, a complete different story, not that dramatic, but anyway, it's something that no matter where you are, it's here. And actually, even more recently, there was another accident similar to the previous one in India that actually had even a more dramatic causalities number. So this is a fact that we need to implement structural monitoring in our system to prevent this kind of extremely deadly causalities, accidents. Of course, not all of them can be as dramatic as those that I just present. There could be failure in a structure that is not linked to human death, let's say, like in this picture in which a windmill collapsed. So even if there are not causality, not dead people, let's say, a failure like this is anyway extremely expensive and extremely bad for any company that works in the field. So what is structural monitoring and how we can improve it? Can improve this system. So the components of the structure monitor is, of course, a structure that we want to monitor. Then we need to install or to use some sensor that detect different parameters on the structure, which could be temperature, humidity, and so on. Then, of course, the sensors need to be read, and the data transferred to a certain position. Typically now it's connected to a network in which the data is then saved on the net, of course. And then, of course, you need to understand the data, interpret it, and come out with results, and use the full information that can be used from the customers or the owner of the implant. So this is much more complicated than how I present it here, because there could be digital twins entering the game, in which the data is fed to a simulation, basically, that with a double ganger of on the structure to improve the maintenance of the structure. But in this presentation, I will just focus on the sensors, and actually I will present a specific sensors. So as I already mentioned, what do we need to sense? There are countless of possible sensors that we can implement in our system, from temperature, humidity, acceleration, vibration, noise, strain. So for a power plant, we can actually monitor the current, tension, to see if there is some weird pattern that happen, or for sensors. So at the end of the story, there is no one solution that fits it all. It really depends on the structure itself, how it's built, which kind of material is built with. So a concrete structure will need to be monitored in a different way than a stainless steel structure. And of course, also the failure mode that actually really belong to the infrastructure, it determines which kind of parameter we need to sense. In the old time, they were all checking the railway and the trains by hitting them with a hammer to hear a weird noise, and they were detecting failure with that. So that's by measuring noise. So this system will not work everywhere, of course. And we want to automatize that and improve it in a digitalization world. So I will focus on the strain gauge. Is of course a sensor that measures strain, so a mechanical deformation. And we focus on this one because it's the one that is linked to many failure modes that are both in industrial, so stainless steel and steel structure, and in the civil engineer environment, in concrete, let's say. So here I just put an example of stress and strain plot of I think is a steel bar. So you can see that it's not linear, it's far to be linear. And what we want is typically to design a structure that keep the working point in the linear range, so before the yield strength. That's not always true, and that's not always that can be changed during the environment, since we don't have full control over the whole environment. So to reach the yield strength, or to anyway induce plastic deformation in the system, will result in different distribution of stress strain that could jeopardize the structure afterwards. And accurate strain measurement could improve our knowledge in this field. So how do we measure the strain with our system? So we differ with what you can find on the market at the moment. What we realize is a MEMS structure in which we have a beam, and we make that beam vibrate. So the resonant frequency of the beam is linked to the material that we are using to make it. It's linked to its geometry and to the loads that we apply on the beam. So if we apply a force or a deformation to the beam, the resonant frequency will shift due to this tension in the beam. And we can actually detect quite accurately the change in the frequency domain of the beam to and link it directly to the strain applied to the system. So we can actually detect in a really precise manner this mechanical parameter. And in the MEMS that we are using, we use single crystal silicon, so a well-known material that is actually the backbone of all the MEMS MEMS, the inertial MEMS that you can find in the market. And it has several benefits. Among them, I can mention that it's a really strong and linear material. So basically, we will not have any yield or plastic deformation in the silicon, which is perfect for a reliable and stable mechanical resonator as this one. So, of course, we need to compete on the market with what we can find on the market regarding the strain gauge. So I assembled this table to compare the different technology and compare them to the state of the art in this specific technology that I found on articles. And I compared different sensors that you can find and buy now on the market. So the most used, of course, that probably you know very well, is the piezoresistive or thin film, which is basically a metal beam, which is a resistor basically, and the resistance will change depending on the strain applied to the beam. It's easy, it's really cheap, but of course, and in the technology from the technology part, the focus was to make it more stable and to improve the stability over time. And here the failure mode is typically due to oxidation of the material. So the main drawback of this is that the piezoresistive is limited by in the sensitivity. So it's limited due to physical property of the material. So it's not the best, even if you can improve the sensitivity by adding different, by arranging different resistors in a Wheatstone bridge. And furthermore, to measure a resistor, you also need to make a current flow in the system and measure it. So it's also relatively power consuming, let's say. The other side, on the other side of the spectrum, let's say, we have optical fibers that basically implement this grating element in certain position of fiber optics. These act basically as a bandpass filter in the light domain, and the frequency that is stopping is basically linked to the gap, the pitch of this line that you can see on the fiber optics. So when the fiber optics is pulled, the interdistance between the gratings will change. So the period of the grating will change, and that will bring a shift in the frequency in the optical domain, let's say. So the concept is similar to what I'm aiming to do for the mechanical resonator. This it's, let's say, the most precise and sensitive sensor up to now, and it's linked to an interferometer approach, which is a kind of expensive and a high-end user sensor. And I also found that there is a macro resonator, so not that doesn't exploit the MEMS capability to miniaturize the system, but it's actually a tiny wire that is vibrating, and they use it as in the same way as I want to use my sensor, which actually have quite a good capability, even if the resolution is not that great. So this is our sensor. So it's, as you can see, it's a simple resonator in which I can have actually the there's a pointer. So it's a beam that is anchored on the two sides here. And we had a lot of design at the beginning, a lot of simulation regarding this, in which we want to make it move only in plane in this direction, so orthogonal to the direction of the beam. And we implement electrostatic actuator as a way to move the system, let's say, because we need to stimulate the system, to the beam, to put it in resonation. And this actually give another good strength point on this technology, in which you can detect immediately if there was a failure in which the sensor is broken, because you will apply a voltage and you will not see any current in the other side. So you will basically detect if there was a failure early on. And another point that I was working quite hard on it is the quality factor of the resonance. The quality factor is basically how pointy is this resonance. And that's linked basically to the resolution, the final resolution of the device. So a high quality factor will allow us to discriminate smaller variation of frequency, and so improve the sensitivity of the system. And that's basically done while packaging the device with a high vacuum, so down to 10⁻³ millibar at wafer level. So the device is packaged and encapsulated in a vacuum at the wafer level. And what you will see basically is a simple silicon brick with some metal pads on it. So here is a first design that we developed here in Syntef, in which instead of having this cap in vacuum, we end up designing an open package, and we create the vacuum at die level. And the way to measure it is basically to apply a voltage, a DC voltage on the beam, a AC, a sinusoidal voltage with a sweep in a certain frequency domain range on one side, and read out through a transimpedance amplifier the output. So we start some testing on the, let's say, non-optimal design, in which it was not encapsulated, and we have seen that there was a resonant peak that shift due to strain, and it will shift a little bit also in due to temperature of the system. So now we have a silicon brick with a mechanical element that is performing really well. But of course, it's kind of useless to have a silicon element standing in the air. We need to attach them to the structure. And for the beginning, we were focusing on die attach to steel and to industrial, let's say, field, in which targeting stainless steel and steel. So we have seen that the tech, also not only the sensor, but also the bonding, it's extremely critical for the performance of the sensor. So we are actually investing quite a lot of effort in optimizing this apparently easy and straightforward task to glue or bond the sensor to a mechanical element. And I will enter a little bit to the details a little bit further on down the presentation. Another part that I already mentioned it can be really critical is that the device that you can see here in a SEM image not only need to be encapsulated in a vacuum environment, but it also needs to be thin. So here you can see the device that is in a package with 60 micron cap. So that means 0.06 millimeter. So it's an extremely thin design that will allow to improve dramatically the readout circuit, the readout of the sensor. So the package itself will affect less the measurement. And of course, as a last building block, we need also to have a readout electronic circuit that enable us to read all these resonance in the frequency domain, and that's, let's say, need to be done in a more compact and less expensive way than the transimpedance amplifier that I was mentioning. So we end up with some electronics, and here you can see there is still a transimpedance amplifier that transform the current in a voltage. And then we end up with some filtering and comparators and a control unit that basically transfer the analogic data that we get here into the digital world, let's say. So the die attach. We were evaluating 3 types of bonding, let's say, from the easy one, that is of course glue, in which we basically want to use an epoxy-based glue to attach it to the part, the mechanical part. The glue is of course easy to use. It's a relatively low temperature process. The bond strength is kind of good, but is not optimal, of course. And furthermore, it's degraded with the temperature and humidity in the environment. So it's not extremely good for high performance and stable sensor. Then we are evaluating the solder. That's another big interesting approach to do die bonding. And it's definitely less sensitive to humidity since it's a metal, basically, material. The bond strength is really good. It's kind of good, but it's more difficult to use and typically has a higher temperature in the process. And the last approach that we are evaluating, which is not mature enough to be implemented in a system at the moment, but it will be big things coming soon, I think. It's the slit bonding, which is extremely high strength, and it's, as the solder is basically insensitive to temperature, since the bonding layer will be a thin layer of metal. But it is of course difficult to implement, and it requires quite a flat surface. So for the moment, we started our work on solder, and we are testing two types of solders. And since we need a full control over the thickness of the uniformity and the planarity of the system, we end up using preforms of bismuth tin and gold tin solder. We are basically at the moment bonding several dies with different parameters to evaluate the planarity and the strength, as you can see on this second image here, where we do a shear testing of the bonded surface, bonded die. The readout electronics, as I mentioned, we have some DC signal that is applied to the beam, and then we end up using this feedback loop that basically will adjust the frequency according to the frequency of the beam. So it basically automatically lock the resonant frequency of the beam in the system, improving quite a lot the readout electronics and the performance. And that's, of course, as I mentioned, it could be digitalized via, at the moment we are using a microcontroller, but of course, all this part can be further improved in commercialization phase of the product. And here, as you can see, a simple check that all the readout electronics works and perform good enough. So here is a first prototype, is a full of wires, of course, but that was then shrink and optimize in a following design of this concept. And here you can see also the sensing element. So this is a ceramic package in which we have a MEMS structure inside that resonate. So you can see the frequency is 10.35 kilohertz for this demo. So a second version after this initial trial of the electronics is basically this one, in which we have all the readout electronics, the analog readout electronics on a PCB. And the sensing element is actually placed on a thinner part of the PCB. This is basically a 50 micron of Kapton PCB with a stress relief structure to avoid that any temperature effect due to the PCB will affect the sensing of the strain in the element at the center. So this is a novel and a quite interesting concept. And here we just receive some initial PCB from the producer, and we are start soldering and assembly the system at the moment. So we need to test this. So actually the electronic itself was already tested now, has been tested during the last week, and we need to assemble, to further assemble the element at the center. So what's the way ahead of us? So this was fully founded internally at Syntef. So there are a lot of improvement that we can think of. Of course, I was the person involved in the fabrication of the silicon element on the sensing element. So on my side, I can say that I can work quite a lot on the fabrication, yield and reliability. There were a lot of novel and really critical fabrication steps in our laboratory that can be improved. So that for sure is up to me, let's say. And then, of course, the packaging. Now we have a packaging that fits a demonstrator kind of approach, but there is a lot of improvement that we can think of. In particular, we need a package, a an outer package that basically fit the specific need of the application that we are targeting. And that's actually really important to tailor the system, the sensor system, to the specific application to get the best result. Furthermore, at packaging level, we can also compensate for the physical limits in the compressive domain of the sensor. So basically, it's a beam that vibrates. So if it will not behave really well once a compressive strain is applied to the system. So due to buckling, basically. So you can design the package in a way that it will compensate for that and shift the range, the working range of the system to where we need it, basically. There are a lot of thermal compensation and pre-stress that we need to apply to the system, and that's something that we need to study now when we have the sensor up and running in a PCB and in a real environment. So that's on the to-do list up in the list, let's say. And finally, of course, at the moment, we are more hardware related, as you have seen from the presentation. So our focus was at the moment on the element sensor and to have a readout circuit that are able to read the sensor, not in a production oriented prototype, but on a research prototype, let's say, to demonstrate that everything works accordingly, and the electronic system itself can be improved in a lot of ways. So there could be the strategy for the to assemble a network of elements. We can of course add different type of sensors, as I mentioned at the beginning: noise, humidity, temperature, and so on. And of course, now there is an emerging technology and field, which is this edge computing. And so you can also think about to put some smartness in the node to improve the time, the lifetime of the system. So there are a lot of interesting fields that we can explore further. And of course, it's everything here is really linked to the application that we need to target. So that was my presentation. So thank you very much for listening.
Thank you, Guido. Then we open up for questions.
Yes.
Maybe some questions out there. Johannes.
Yeah, very interesting. I like to see that we really work with good electronics and start with a good solid fundament. But I was thinking, since I'm coming from Hydro and industry, we need to bring this kind of technology readiness level up to practical use when we're going to use this into our system. So have you thought of a process making this as a product, or join a company who will help you with the commercial part of it? Or
so now it's of course is on the table. We would like to finalize and to record. So this is the second year of this internal project. We have a batch of sensor that is in the lab now, but it's in the last phase. And I would like to basically have enough data to convince people that this works and that could be beneficial for a lot of people. So the competition is of course really harsh because they are already there on the market. So to enter in a new market, well established with this cheap option, let's say, it's tough, I think. but there will be for sure room to have industrial partner for this. Yes.
Have you thought about interfacing this to wireless system or 5G,
yes,
or easy adaptable for kind of this?
Yeah, as I mentioned, the readout electronics now is really for a demonstrator kind of. So the important thing is to extract data, and one of the most important thing that we were targeting is the stability over time. So that's why we don't want to use glue, because even if for a demonstration, let's say for a short video, it will be enough. But if we target a long time period, the drift in the performance will be dramatic. So that's one of the things that we want to avoid, to target, let's say, higher end. And I didn't mention it, but of course, the idea is to have the sensor up and running in an unmanned way. So the people will not be there to look at the sensor every day. So the system should work properly without a person there. And you can collect and study the data, reliable data from your office. That's one of the most important things.
So you need anomaly detection algorithms on this system to monitor it and learn, have a kind of learning system to see what failure modes will be applicable.
Yeah, this structural monitoring is of course extremely important, but is also extremely expensive because it should specifically target the structure that you want to monitor. So there should be a cohesion between the producer of the structure, the owner of the structure, and the sensor and IT guys that need to get an agreement on what to do and how to do.
Yeah. Thank you and good luck further.
Thank you very much, Johannes.
Yes. Any more comments or questions? No. Okay, Guido, then I just say thank you for the very, very interesting presentation. So
thank you very much for that.
Yes, and thank you to all.
It was a pleasure.
Yeah, thank you. And thank you to all of you for attending. Okay.
Thank you.
Bye.
And have a nice day. Bye.
Have a nice day. Bye-bye.
Bye-bye.